Welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of computing professionals and students. I'm Marco Kutese, Professor of Electrical and Computer Engineering at Rutgers University's Wireless Information Network Lab. My research interests are in the area of location privacy and wireless systems, including work on connected vehicles. I'm an ACM Distinguished Scientist and currently serve as Chair of ACM SIG Mobile. I'm also an ACM member. To learn more about my background, please check out the bio widget on your screen. For those of you who are less familiar with ACM or what it has to offer, here's a bit more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. And you can see some of these highlights on the screen. For example, ACM provides timely computing information, including the communications of the ACM and Q magazines, the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts, support for education and research, including curriculum development, teacher training, the ACM Turing Award, and ACM Prize in Computing Award, and the newly updated ACM Code of Ethics, a collection of principles and guidelines designed to help computing professionals make ethically responsible decisions in professional practice. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items that are shown on the slide in front of you. First, the slides will advance automatically throughout the event. And on the bottom, you can find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows or Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can just close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have questions during this webinar, please type them into the Q&A box at any time during the webinar and click the submit button. I will organize the questions while Andrea is speaking, and I'll reserve time at the end of the presentation to address them. This session is being recorded and will be archived. You'll later receive an email notification with how to access that. You can also check learning.acm.org for updates about this and upcoming webcasts. And at the end of the presentation, you'll see a survey on your screen. Please take a minute to fill that out. You can use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. We'll be watching for your tweets. We'll also have a new community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during the Q&A session. Today's presentation is The Future of Wireless and What It Will Enable by Andrea Goldsmith, based on her 2018 ACM Athena lecture. Andrea Goldsmith is the Stephen Harris Professor in the School of Engineering and a Professor of Electrical Engineering at Stanford University. Her research interests are in information theory, communication theory, and signal processing, and their applications to wireless communications, interconnected systems, and neuroscience. She founded and served as Chief Technology Officer of Plume Wi-Fi, formerly Accelera, and of Quantenna. She currently serves on the board of directors for Medtronic and Crown Castle Inc. Dr. Goldsmith is a member of the National Academy of Engineering and the American Academy of Arts and Sciences, a fellow of the IEEE and of Stanford, and has received several awards for her work, including the IEEE Sumner Technical Field Award, the ACM Athena Lecturer Award, the ComSoc Armstrong Technical Achievement Award, the Voice Mentoring Award, and the Silicon Valley San Jose Business Journal's Women of Influence Award. She is author of the book Wireless Communications and co-author of the books MIMO, Wireless Communications, and Principles of Cognitive Radio, as well as an inventor on 29 patents. Dr. Goldsmith has served in a variety of senior roles with the IEEE Information Theory and Communication Societies, as well as at Stanford. In these roles and others, she has demonstrated a commitment to inclusion and diversity in technology and women in leadership roles. After receiving the 2018-19 ACM Athena Lecturer Award, Dr. Goldberg established the ACMW Rising Star Award, recognizing the outstanding accomplishments of young women researchers in computer science and related fields. She is also an ACM member. For a full bio, please check out the widget on your screen again. Andrea, without further ado, please take it away.
Okay, thank you so much, Marco, for the kind introduction, and thanks to everybody for logging in this morning for this talk, or afternoon, depending on what time zone you're in. It's really a pleasure to be giving this webinar, and it is based on the ACM Athena lecture that I gave at Mobicom in Delhi. So let me move to the beginning of the talk. So basically, I want to talk about future wireless networks. It's always a little bit dangerous to talk about the future because people can come to you 10 years later and say you got it all wrong, but I'm going to go ahead anyway and take a stab at my vision for future wireless networks. And I've been working in wireless my entire career since the mid-'80s, so even before we had cell phone technology and Wi-Fi. And I actually believe that this is the most exciting time in wireless communication. And the reason is that the early generations were on the 5th generation now, or 6th generation of Wi-Fi. But for the most part, those early generations of systems were really focused on people communicating with each other or people accessing information over the internet. And what's new with the current generation and future generations is much more device communication. So basically, people are out of the loop, and we're going to see a lot more devices that are communicating with each other, sending information up to the cloud for extracting important information, and so forth. This opens up a very exciting range of new applications, everything from autonomous driving to smart cities, networks inside and around our bodies, and many, many more things. And so I think that what we're going to see going forward in terms of what wireless can enable is a really exciting vision, and I hope to share that with you through this webinar. Okay, one of the biggest challenges for wireless communication, which has actually been the case since the first cellular phones were deployed, analog cellular in the 1980s, is the lack of spectrum. So this slide shows a graph from an FCC report that was published a few years ago, showing that basically as of 2013, the licensed spectrum for cellular service, even if all of that spectrum was upgraded to LTE, which is the current standard for cellular, is full. And in fact, as of 2013, we were 90 megahertz in spectrum deficit for the demand for wireless data, driven primarily by video. Now, you might say, well, if we were in 90 megahertz of spectrum deficit that long ago, why are we still able to use our wireless devices? And the reason is Wi-Fi. In fact, Wi-Fi has 300 megahertz of spectrum in the 5 gig bands and about 80 megahertz of spectrum in the 2.4 gig bands. And that's why, for the most part, when we want to use high-speed wireless data, we go to Wi-Fi, both because it's cheaper, but also because there's a lot more spectrum up there. In addition to Wi-Fi, we have new bands that are coming online in terms of millimeter wave. Hang on a sec. where there's tens of gigahertz of spectrum available, and we're starting to see some millimeter wave deployments. And then we also have molecular communication. Now, this isn't really part of the typical wireless paradigm, but it is a wireless network, and I'll talk a little bit towards the end of the presentation about some of our work in molecular communication. Now, if we're in spectrum deficit now, just in the license bands, one of the big questions is how are we going to support new things like the Internet of Things, which is predicted to have billions, tens of billions of devices by next year. And before I talk more about what the Internet of Things is, if you believe this prediction, then we need to find ways to support devices of this nature because they can't be supported in the existing license bands. Now, one of the interesting things about the Internet of Things, and I'm going to talk a little bit more about that on the next slide, is that the requirements for the Internet of Things are very different than smartphones. So up until now, smartphones have really driven the growth of wireless data demand, both on cellular networks and on Wi-Fi networks. But the Internet of Things, which is going to enable this smart sensing and automated driving and virtual reality, have very different requirements. So in some cases, if it's a small, low-powered sensor, the data rate requirements are low, but these sensors are very much driven by their energy consumption, which is a constraint. And therefore, we need to build wireless networks that are much more energy efficient from the device perspective than the existing networks. When we're trying to do things like real-time control and self-driving cars, we need extremely low latency, much lower than what's possible in the 4G networks of today. So this growth of the Internet of Things is not only going to require more spectrum to support these devices, but it's also going to require a different type of network that can continue to support the requirements of smartphones, which are going to be, continuing to demand massive amounts of data, but also small sensors that have lower rates, but energy consumption constraints, and latency associated with real-time control. Okay, so let me now just talk for a moment about the Internet of Things because it's been a term that's buzzword that's been pervasive in wireless communication, but I rarely see people actually define it. So I just want to say my view of the Internet of Things, which is enabling every electronic device to be connected to every other electronic device and to the Internet. So of course we already have devices like that, smartphones, consumer electronics with Wi-Fi, cars which are connected. These are all part of the Internet of Things today. But what's going to be different going forward is that many, many more devices, things like clothes, medical devices, lights, thermostats, pretty much everything with an on-off switch is going to be connected. And the beauty of that paradigm is that we can collect massive amounts of data from these devices, do data processing in the cloud to extract important information, and that is the value in the Internet of Things. So it's not valuable that my tennis shoes can talk to somebody else's tennis shoes. What's valuable is collecting that information from my tennis shoes and telling me something about my health and wellness, how much exercise I've done in a given day, or collecting data from medical devices in and around my body so that I don't need to go to the doctor to have standard medical checks on heart rate and things like that. Now, the Internet of Things is a buzzword, and having been in wireless since the 80s, I've seen a lot of hype around sensor networks and ad hoc networks and many types of wireless networks, which kind of, died away after a few years. But I actually believe that the Internet of Things is a very powerful paradigm that's going to drive innovation in wireless. And the reason for that is that we're already seeing verticals that are making money off Internet of Things type applications. Everything from security and surveillance to industrial applications, health and wellness, consumer. So the fact that today we have markets for Internet of Things applications means that maybe these won't be the killer applications of the Internet of Things going forward. Maybe some of these will go away. But given that people are making money today off the Internet of Things, leads me to believe that it's going to be a very strong driver of future wireless networks. Okay, so I showed you a graph a few slides ago showing that the licensed airwaves are full. And so one question, as someone who works in information theory, which was originated by the father of information theory, Claude Shannon, is when you look at that graph, question that I would ask is, are the licensed airwaves full because we're at the Shannon capacity of that channel or that amount of spectrum, or is it that we're just not designing systems well and we could be orders of magnitude away from the Shannon capacity of that spectrum? So that's the kind of question that an information theorist would ask. And I've actually worked on the Shannon capacity of wireless channels my whole career, starting in graduate school. And the beauty of working in that area is that we don't know the Shannon capacity of most wireless channels. So we can't answer the question whether the spectrum that's been licensed today or the Wi-Fi spectrum is actually at capacity, or if we're just not designing systems well to reach the capacity limits. And when I say we don't know the Shannon capacity of most wireless channels, certainly when we don't have a channel model, which is true for molecular channels as well as millimeter wave and terahertz channels, we don't have good models for those channels because they're relatively new, we can't determine the Shannon capacity of a channel if we don't have a model for it. If you look at time-varying channels, this is something I did all the way back in my PhD research, we don't know the Shannon capacity of most time-varying channels unless we know the channel perfectly at the transmitter and receiver and adapt to it. Other than that paradigm, the capacity of most time-varying channels is unknown. As soon as we go to systems where there's interference or relaying, the Shannon capacity of both of those channels has been an open problem for decades. And cellular systems actually introduce interference through channel reuse. So if we don't know the capacity of channels with interference, we don't know the capacity of cellular systems. Ad hoc networks introduce relaying. Sensor networks are a particular type of ad hoc network, so we don't know the capacity of those networks. And perhaps most importantly, one of the beautiful things about Shannon capacity is that it assumes infinite delay, infinite computational power, and infinite cost in terms of the complexity of the system. And so as soon as you put constraints on any of those three dimensions, we don't know the Shannon capacity of those channels. Now, you might say, well, why waste time working on Shannon capacity when all these problems are open? And the reason that I work in it is because it really provides not only upper bounds on performance, but it also provides a lot of design insights. And I would argue that the most powerful wireless systems that we have today, the techniques that we use in both cellular and Wi-Fi at the physical layer as well as for multiple access, are based on the insights that came out of Shannon theory. Okay, so looking at enabling much higher data rates for this next generation of networks, 5G networks, both Wi-Fi and cellular, there's a couple of enablers, and I put them in two different categories. One is in the network design, so actually rethinking cellular system design. And that leads to a paradigm that I call software-defined wireless networking. So I'm going to talk about that in a few slides. But first I want to talk a little bit about enabling higher data rates just at the physical layer or through multiple access techniques. And the way that we do that at the physical layer is, first of all, if we have more spectrum, we can get higher data rates because we're utilizing larger bandwidth channels, and those have higher data rates. We can also use many, many antennas, a technique that's called massive MIMO. There's also new modulation, coding, and detection techniques and new multiple access strategies. Now, whenever I say, and I know most of the people on this call are more in the computer science field than electrical engineering, but in electrical engineering, if you say, oh, we're going to design new physical layer techniques for wireless, people say that field has been completely depleted of new ideas. And in fact, the first time that was said was in 1971 at a workshop called Coding is Dead, a talk called Coding is Dead by my former colleague Bob McLeese. And so in 1971, even though there'd been all this beautiful coding theory, there was no way to implement it given the technology of the time. And Irwin Jacobs got up at the end of that talk and he pulled out a small VLSI chip and he held it up and he said, coding is not dead, and this is why, because we have massive computational power that's coming through new technologies. And I think whenever you say that a technique is dead, it may only be dead temporarily, because as technologies evolve, you can actually revisit many of the techniques that seemed impossible to implement at the time. That's what happened in 1971. It happened again in the 80s, just before cellular systems took off. In fact, AT&T moved their whole team of engineers that had been working on wireless communication to optical fiber, because a famous management company, McKinsey, told them that there was no future in wireless. Then the first cellular systems came out, and wireless was not only not dead, but it was super exciting, and there was a lot of exciting problems to solve, both in Wi-Fi and cellular, through the early generations of both of those systems. And then about 5 years ago, I would say that people thought that the kind of wireless physical layer and multiple access was dead, because we had LTE and there wasn't a lot of excitement. It was kind of viewed as mature. But now with 5G and all of the exciting things that it can enable and the new requirements for 5G systems that aren't supported by 4G, it's actually risen again, and there's new things to do at the physical and MAC layer, as well as in the wireless design. So I want to just talk for a moment about two of the most exciting technologies at the physical layer, which is bringing together millimeter wave as well as massive MIMO. So millimeter wave is using spectrum in the tens of gigahertz range, so 60 gigahertz, 70 to 80 gigahertz. There's tens of gigahertz of spectrum up there, so all of the existing licensed spectrum for all wireless systems would fit within the bands available in the millimeter wave, and it's also lightly regulated, so it's very exciting spectrum to use. Now, the problem with millimeter wave is that power falls off inversely proportional to frequency, so as you go up to these high-frequency bands, you limit range if you only use a single antenna. So even though you've got a lot more spectrum, you can only use it at a very limited range. The way to get around that is something called massive MIMO, which is where you have hundreds of antennas at the base station, and those antennas can actually form a pencil-thin beam to talk directly to the wireless device. And by doing that, you actually get around the problem of this power falling off inversely proportional to frequency squared. So you can get very high range by going to these large antenna arrays. Now, that works in theory, but in a real channel, you may have a building that's blocking that pencil-thin beam. That causes scattering of the ray, and then you run into a lot of challenges in using massive MIMO. So these are some of the things that researchers are looking at for 5G communication. There's also a lot of challenges in doing this massive MIMO, which is first estimating the channel, because you have hundreds of parameters to estimate associated with the hundreds of antennas. You need to know exactly what the channel gains are for each antenna in order to form that pencil-thin beam. The complexity of the algorithms to do this kind of beamforming is also very high. And then, of course, there's the propagation challenge of the scattering that I just showed. One of the things that my research group has been looking at recently is using machine learning in wireless systems. Now, I don't tend to be a bandwagon type of researcher, so if there's many people that are working in a particular area, I tend to go a different direction. But it turns out that machine learning is the only way to solve for some of the challenges that we have in our molecular communication systems, because there's no channel models. And machine learning works extremely well in systems where there's no model. So that's what got us interested in machine learning applied to wireless communication. And what we actually have shown is that machine learning trumps theory. It beats the theoretically optimal technique when the channel is either unknown or there's a complexity constraint such that optimal Viterbi detection is impossible due to the complexity constraint. So we've actually shown that machine learning can work better to equalize unknown or complex channels than standard Viterbi detection, which is optimal when the channel is perfectly known and there's no complexity constraints. We've also looked at machine learning in joint source and channel coding of text, and it actually beats standard compression techniques applied to text followed by standard channel coding. There's so the fact that we were able to do better than known optimal techniques in both of these cases caused us to think about other ways to use machine learning in wireless system design. And so I have a list of different things that we're looking at, and I won't go into the details, but suffice it to say that, in fact, much to my surprise, machine learning is actually a very powerful technique for a wireless system designer to use. It doesn't always beat theoretically optimal techniques, but we actually know when it does based on the work that we've done so far in certain domains. Now, I want to move away from the physical layer and talk a little bit more about cellular system design in general. One of the interesting things to me about cellular system design is that the fundamental principles behind it, which is that you have base stations in the middle of each cell and you reuse channels. Now we do it every cell. We used to do it over a larger number of cells. But this whole premise is based on a paper that was written in the 1940s. And so we haven't really revisited the overall design of cellular systems, even though the physical layer and the multiple access techniques have evolved tremendously, obviously, from the 40s to today. So when we think about how to redesign cellular systems based on all the sophisticated techniques that we have at the physical layer, not only should we kind of start with a blank slate. That's what you can do when you're a researcher, obviously. If you're building these systems or you're running these systems as an operator, you can't start from scratch, but as a researcher, you can, and say, you know, how much are we leaving on the table in terms of the way that we're designing these systems? Is there a lot more capacity that we can get out of them? So that's one question that we can ask. But again, as we think about what we're redesigning for, we're not just designing for smartphones that will have higher and higher data rate demands. We're also thinking about applications where energy constraints are the driving force, or where coverage is extremely important. I mean, it's funny to me. I live in Menlo Park, right off Sand Hill Road, some of the most expensive real estate in the world, and whenever I drive up to the freeway, my cell phone voice call gets dropped because we still don't have good coverage due to trees and mountains and so forth. So that's not going to be acceptable when we're using cellular systems for control, real-time control and autonomous driving and so forth. So with recent technical advances, the old ways of thinking about cellular system design, which is that we reuse channels, that causes the system to be interference limited, and therefore we need to design an interference limited system. That's no longer the case once we go to MIMO techniques, where we remove interference by pointing beams in very specific directions, or using multi-user detection techniques to get rid of interference, or having base stations cooperate so that interference doesn't really exist anymore. And in terms of thinking about applying all of these new techniques to cellular system design, we also need a cellular system that's much more dynamically optimized through something called self-organizing networks, or SON. One of the other big developments in cellular systems is the use of small cells. This is something that I actually started working on very early in my academic career when I was at Caltech in the mid-90s. And we basically showed back then that using small cells provides exponential capacity gain. As you shrink the size of a cell, the capacity that you get in the system overall increases exponentially. And I don't have time to explain why, but it's a pretty simple explanation. So if you believe that, then the way you might say, well, then why don't we design cellular systems with just small cells? So in terms of the difference between a small and a large cell, a macrocell is usually placed on the top of a building, and it has a radius of, you know, about a mile or a kilometer, whereas a small cell is placed much closer to the ground, and it may cover a few city blocks. So you might say, well, why don't we just design systems that are only consisting of small cells, because that's how we get the highest capacity. The problem is that it takes a long time to deploy enough small cells to have universal coverage. So the way cellular operators are deploying new networks is you put up large cells, macrocells, for coverage, and then you fill in with small cells for capacity, And you also get power efficiency from that because the antenna is much closer to the device, so the device doesn't need as much power to reach the base station. Now, how do we optimize the resources associated with all of these base stations, whether they're small or large? The best way to do it is to do it in the cloud. So the idea for an LTE system is that you have large cells and small cells and maybe femtocells, and the cloud is basically collecting all the information associated with the users. In fact, I'm going to go back one slide. So the cloud optimization here is collecting all the information from the base stations, large and small, and optimizing which channel the macroscale should operate on, which channels the small cell should operate on, things like power allocation. They can optimize even multiple antenna parameters. And so basically, by doing this centralized optimization, you're optimizing the performance and efficiency of the resources available to the network. Now, you can think about doing that not just for LTE, but for other wireless networks as well. And in fact, my second startup, Plume Wi-Fi, that was the premise, was that you could take all these heterogeneous Wi-Fi access points, have them send their information up to the cloud, and then the cloud does the optimization across the Wi-Fi access points so that you limit the interference they cause to each other. So you can do that with Wi-Fi, and you can do that, in fact, with any wireless networks. Any wireless network. And in fact, the cloud not only optimizes a particular network, like a Wi-Fi network or an LTE network, it can optimize across these networks as well. And that leads to this notion of software-defined wireless networking. So the idea here is that you've got different wireless networks at the bottom level, whether it's Wi-Fi or cellular or millimeter wave, maybe satellite networks as well. And this unified control plane is not only allocating resources within each of these networks, as well as across them. So, for example, if cellular networks move into the Wi-Fi unlicensed bands, you could use this unified control plane to manage the use of the unlicensed bands between Wi-Fi and cellular, because there's a lot of concern about cellular being the 300-pound gorilla that's going to knock Wi-Fi out of those bands. So not only can the unified control plane optimize resources across these networks, but it can also tie the application to the best network. So, for example, if you're doing AR or VR, which has a huge bandwidth requirement, you might have that application run on a millimeter wave network where there's a lot of spectrum, as long as that millimeter wave network was available. But if the user of the VR moves out of the range of the millimeter wave network, then the control plane can hand it off to cellular, and of course there would be a commensurate reduction in range. And in fact, if you take this vision of software-defined wireless networks one step further, you could say there are no actual networks. We just have a bunch of distributed antennas at different frequencies, and the unified control plane figures out how to best use those antennas from the physical layer all the way up to the application layer. So that's my Shangri-La view of software-defined wireless networks. Now, of course, there's many challenges associated with this. The algorithmic complexity in particular, when we try to do centralized optimization, often even simple resource allocation problems like frequency allocation. This is something that 2G wireless networks, the first digital wireless networks, was trying to do channel allocation, and that's an NP hard problem in a cellular network. So now that was second generation cellular. Now we're all the way up to fifth generation cellular, where we have multiple antennas and power control, large and small cells. This becomes an NP really hard problem, so we can't solve it in closed form. But we do have advanced optimization tools to solve these complex optimization problems. But one of the things that we don't get, even if we use these powerful optimization techniques, is we don't get around the latency of sending the information up to the cloud and the complexity of solving this hard optimization problem in the cloud. So one of the other things that we've looked at recently is something I call fog optimization. In fog optimization, basically you define a neighborhood of base stations, and you do the optimization within that neighborhood, and then each neighborhood does its own optimization. So if you shrink the size of the neighborhood down to a single cell, it's fully distributed optimization. If you grow the size of the neighborhood up to the entire network, then it's fully centralized. So by changing the size of this neighborhood, you can scale the complexity and latency of the optimization depending on the neighborhood size. And by the way, in addition to the optimization, we can also use similar techniques to look at things like optimizing caching at the cell edge as well as edge computing. So we've actually done some work on this fog optimization versus centralized. So these slides show on the bottom left if we're just doing single user decoding per base station, and the slide on the right shows joint decoding where you have a much more powerful mechanism to deal with interference because you're jointly decoding all the signals so they don't interfere with each other. And I'll just say that if you go from fully centralized to fully distributed in the picture on the lower right, you have an order of magnitude loss. But we see that in the middle, by having a few neighborhoods, you have much less than this 10x loss and much lower complexity and latency because you're doing the optimization in a smaller set of base stations versus fully centralized. And I'm happy to come back to that if there are questions later. Another important element in the next generation of wireless network design is the notion of green cellular networks for the IoT, because these devices, or at least many of them, are extremely constrained in terms of their energy consumption. And so we not only need to design cellular networks that are going to require minimum energy of the end devices. Some of these devices may never be recharged versus a cell phone, which you can recharge constantly. And some of our research has shown that by thinking about energy consumption rather than capacity or rather than high data rates in the design of these cellular networks, we can get easily an order of magnitude reduction in the energy consumption requirements of the devices. Now, when we think about where energy should come from, of course, we traditionally use batteries and plugging our devices into the phone or into the wall. So this is well understood. That's the paradigm we've used for both Wi-Fi and cellular for decades. Another thing that we could do is transfer the power wirelessly. This is a technique that's poorly understood, especially at large distances and with high efficiency. But if we think about sending signals to devices, those signals contain energy, so why can't we somehow harvest the energy in the signals that we're sending to help devices recharge themselves? And you can also harvest energy from the environment through vibrations or solar or other ways, from somebody walking around. They can actually charge their battery, although, again, it's not very efficient. And this requires a new communication paradigm because you no longer have a constant source of energy that's available. So these are some of the interesting topics being considered in looking at where energy should come from these very energy-constrained devices. I'm going to talk very briefly about chemical communications. So the idea of chemical communications is that rather than using electromagnetic waves to send ones and zeros, to send bits, we use chemicals. And you can do that through on-off keying. So you send a chemical to indicate a 1 bit, and you send no chemical to indicate a 0, or you can use different chemicals. And the thing I love about this research area, it was started by a postdoc who joined my lab a few years ago, is that it's a completely greenfield area of research. Everything about the design of this system is new. And so we've done some current work on this, dealing with the fact that the chemicals dissipate very slowly. And this is where we've applied the machine learning because we didn't have a model to do equalization. We don't have a channel model. These are systems that are not driven by Maxwell's equations. They're driven by diffusion equations. And there's actually a fun article in the Stanford report from a couple years ago talking about our system where we're sending text messages with Windex and vinegar. One's an acid, one's a base, so they cancel each other out. And the article said that this is not likely to replace texting among Stanford students in the near future, but maybe sometime farther out. And the last thing I'm going to talk about is the brain as a communication network. So basically, if you look at how neurons communicate with each other, it's not a wireless network, it's a wired network using electrochemical signals. And we actually did some work on this with a colleague in the med school, Yosef Parvizi, who's an epilepsy specialist, looking at how to determine the seizure onset zone of epilepsy. So the way an epileptic seizure happens is that there's a neuron within the brain, which is where the seizure onset zone is. It starts oscillating. That oscillation travels to surrounding neurons through this electrochemical channel. Then those neurons start oscillating, and eventually the oscillations propagate out to a sufficient number of neurons that there's a seizure. And the way that the doctors treat this if the epilepsy is drug resistant is they put these ECOG sensors on the surface of the brain under the skull. They look at the readings of the ECOG sensors, which is in the middle, and somehow the doctor, based on looking at that, sees where the seizure onset zone is. So we actually applied signal processing techniques based on directed mutual information to estimate the seizure onset zone just from the data, and we actually beat the doctors. So what you see on the lower right is the doctor identified seizure onset zones are in green, and the ones that our algorithm identified are in purple. So it overlaps with the region that the doctor identified, but it's actually more specific. So to summarize, this is a very exciting time to be in wireless technology. It will enable new applications that will change people's lives worldwide. I'm not just saying that because I want to get funding. I think this is really true. Another exciting aspect of the future wireless networks is that there's new paradigms. Not only do we need to support high data rates for smartphones, but also extreme energy efficiency. And finally, we can use the tools of communications and modeling that we've been using to design wireless networks and apply them to other areas of science, such as neuroscience. So with that, I'll wrap up and happy to take questions. Thank you so much for your attention.
Thank you, Andrea. Let's move on to questions. We have a number of questions in the queue, and I'll be grouping them a little bit to try to answer as many of them as we can. Let me start out by asking you about your comments regarding the additional requirements coming in from IoT applications in terms of energy and latency. And you described that we don't even have a great understanding of channel capacity limits yet in many practical settings that have been studied for a long time. How would you characterize our theoretical understanding of the energy limits and of issues such as energy and latency?
Yeah, that's an excellent question. So on the energy side, as I said, we don't, let me go back to the Shannon capacity, because if you look at Shannon theory for trying to understand what are the fundamental limits of, this is my last bullet here. So when you have delay constraints or energy constraints, you need to come up with a new theory that's moving a little bit away from Shannon capacity. And that's very hard to do because Shannon just created this amazing theory that allowed us to distill down what was most important about a channel model to come up with its capacity. So I've done some work on fundamental limits of energy-constrained channels. There's also some recent work on finite block-length codes, which tie into delay a little bit. But I would say that we are still lacking a powerful theory to understand the fundamental limits of wireless channels when they have delay constraints or energy constraints or complexity constraints. So that's an open area, in my view.
That makes sense. One technology that has been trying to address a part of this IoT space is LoRa, the long-range radios. And what is your view of the future of such technology, and do you have any thoughts on why this technology appears to be more prevalent outside the U.S. rather than inside the U.S.?
Yeah, it's interesting. I'm not that familiar with the long-range radios or why they're more prevalent in Europe, but I think that one of the ways that you get range is directivity. So, for example, that's one of the things that the massive MIMO does, is it allows you to point a signal in a particular direction, and therefore you get much longer range in that direction. The problem is that you need to know what you're talking to. And so if you're thinking about a network, you may not know where all the devices are. Or if you need to do some kind of control mechanism among all the devices, talking to only one device doesn't work very well. So in general, I would say that massive MIMO is a technique, that it's not called long range or LoRa, but it's a technique to get increased range. But in the process of doing that, there's a trade-off, which it makes your network less flexible, because now you need to know exactly where you're talking to. If a user moves, then you need to change all the parameters to continue to point to them. And so I would imagine that, and again, I'm not that familiar with LoRa, but I think that the problem with a system like that is its inflexibility in having to know exactly the direction that it's pointing to, and not being able to communicate beyond a single device that's in that particular position.
Thank you. I guess the opposite trend of the such longer range communications is the small cell trend that you alluded to, and the large capacity gains one can reach with that. That seems to be one core direction for future wireless systems. And one question here is, how does that impact rural environments?
Sure. That's an excellent question. So it's interesting, because as someone who worked in small cells going back to the 90s, I've been waiting. It's kind of like waiting for Godot. I've been waiting for small cells to take off because they provide so much capacity gain. And the reason that they didn't take off up until now is twofold. One is because of Wi-Fi, because Wi-Fi really is a small cell, and so that's where all the capacity gains have come from. The other reason has nothing to do with well, it's not nothing to do with technical, but getting locations where you can put these small cells, getting fiber to the small cells so that they can be part of the network. There's a lot of kind of challenges in building out a network with small cells that have nothing to do with the optimization challenges that I have on this slide. So rural networks will not be affected by small cells, in the sense that in a rural network where you don't have as much demand for data because there's fewer people, the macrocells will continue to service the rural users. And that's why hierarchical networks are so important, because in areas where you don't have a lot of demand, whether it's rural or even a city in the middle of the night, you can use macrocells only. When you go to, downtown New York or downtown San Francisco, and you need higher capacity than a macrocell can provide, that's where you fill in with small cells. So the beauty of this hierarchical approach is that you can continue to get countrywide coverage through macrocells, and then you just drop in the small cells in places where you need more capacity than the macrocell can provide. And in fact, based on the work I do in Crown Castle, they're rolling out a large number of small cells, and so we're actually, and I'm sure that other parts of the world are as well, but we're finally starting to see small cells gaining a lot of traction in the rollout of cellular networks now.
Now, as cellular operators rolling out these small cells, will that become a threat for Wi-Fi technology? How do you see these technologies play together in the future?
Right. So I think that I'm going to go to this slide. So as someone who, both my startups were in Wi-Fi, I do think about, is there a threat? And actually, I think the two networks are very complementary. Cellular provides coverage everywhere, and it allows you to do seamless handoff between base stations. Wi-Fi has a lot more spectrum, but it has to be shared. It's unlicensed. The range of Wi-Fi is generally a lot lower than cellular, and unless you have an enterprise system or something like this software-defined wireless network, you can't do seamless handoff between Wi-Fi access points. So they serve different roles, the two networks. I believe they're complementary. The only threat that I see is if cellular moves very aggressively into the unlicensed bands, because much of the unlicensed bands, at least in the 5 gigahertz range, are lightly used, so there is still plenty of spectrum that cellular systems can use. But if cellular moves into the unlicensed bands, they have an unfair advantage because they also have licensed bands. That could actually hurt the performance of Wi-Fi. So that's the only threat that I see. But in terms of, one system dominating the other or one system going away because the other one is so powerful, I don't think that's going to happen just because of the nature of cellular systems are operator-owned. They're centrally controlled. Wi-Fi, anyone who puts up a Wi-Fi access point has a Wi-Fi network. So I think they're very different systems. They serve very different user requirements and needs, and I don't see that changing in the near future.
Do you see the differences depending on application area? For example, a related question is in the vehicular space and that debate between DSRC, which is perhaps closer in spirit to Wi-Fi, compared to the cellular vehicle communication technologies.
Right. So one of the challenges in vehicular networks is being able to guarantee performance, because if you drop a packet watching video on your Wi-Fi, it's not a big deal. You just have to watch the little circle go around the screen until it comes back up. Whereas if this is a real-time control system, that can have life-changing consequences through crashes and things like that. So the argument there that cellular is generally used is that it's, they own the spectrum, they control the spectrum, they control the entire network, and therefore they can provide a higher quality of service. They're more likely to be able to guarantee the requirements of real-time control, for example, than a Wi-Fi system which is operating in the unlicensed bands and doesn't have the same level of control that cellular does. So I think that that's a fair argument. On the other hand, if you have a lot of spectrum, you can build in a lot of redundancy through coding, through using different channels. So it's not completely clear to me which of those two networks, cellular or Wi-Fi, would actually do better in a application like that. And I think that people will build these networks both in the unlicensed bands and in the cellular bands, and we'll see which one works better. So I think that either network might be the winner, and it depends, devil's in the details, what specific application, where are you running this? Is this in the middle of a city? Is it in a rural area? But I could see both of those networks possibly being able to support that kind of requirement as the networks evolve. Today we can't really do that with either 4G or Wi-Fi, but I think that there's certainly enough technical innovation that we could apply to those network designs so that either one of them could support it.
So most of the wireless networks we are currently using are primarily access networks where we communicate wirelessly over a short distance, and then a cell phone call or cellular data communications still travels largely through wires. To what extent do you see a future where such longer range communications are also transported fully wirelessly, perhaps over ad hoc networks, either file level or MAC layer, or at different layers as well?
Okay. So it's interesting that satellite networks are actually making a big comeback. I was around during the Iridium days, which was a satellite network that was going to provide global coverage. It was going to compete with cell phone technologies. This was the early 90s. It was a very dynamic and exciting system. but the finances just didn't pan out, and it ended up going bankrupt. I think now we're seeing a resurgence of satellite because satellites have a lot of benefits in terms of providing global coverage. And so I think satellites will become more a part of the backbone, but at the end of the day, wireless networks just can't compete with wired networks in the sense of we have fiber optic for wired, and that has gigabit per second data rates, no interference, can travel very long distances. So I think that, and if you look at ad hoc networks, they've never been able to perform very well. It's a very challenging design because every time you go through another hop of the ad hoc network, you lose half your capacity because it's a half duplex relay. And again, there's techniques like full duplex relaying, but it hasn't really panned out that well in practice. So I think that in all networking design, wireless and wired, as soon as you can get to a wired network, you're generally better off using that wired network for transport. Not always, but most of the time. And so there will be scenarios where there is no infrastructure or it's too costly to put up infrastructure, and then you'll have all wireless networks. But I think that for the future that I foresee, we will always have wireless networks that use wired networks for the backbone due to their superior performance.
I'd like to talk a little bit about the future applications of wireless technology that you've mentioned. For example, in the health space, you talked about epilepsy and other applications. Can you elaborate on this a little bit?
Okay, so the work that we're doing on epilepsy isn't really an application of wireless. It's more taking the tools and modeling techniques that we've used over the last few decades to build the wireless networks that we have today and applying them to completely new areas. So I believe that medicine and healthcare have tremendous potential for engineering approaches of modeling, of real-time control, of signal processing to transform the way we do medicine and healthcare. And so the work on epilepsy was just my first foray as a researcher into that area, but I think there's massive other applications of our engineering tools to medicine, and that could be a whole other talk, but things like precision medicine, understanding how drugs are working by using imaging and other types of techniques, the list goes on and on. So it's not so much that that work is an application of wireless, but where wireless does come in to health and wellness is having sensors in and around our bodies to use for medical purposes. So one example, people often ask me how the molecular communication, what is the killer application for molecular communication? And I think, in my opinion, it may be for communicating inside the body, because it's hard to build radios that can communicate in the body, and yet cells communicate via chemicals now. So we could easily communicate via chemicals in the body if we could harness the right technologies to do so. The data rates are very low, but that's okay, because often what we want to communicate inside the body is something like change the level of dosage of a particular drug delivery system, or you want to send a message to an artificial organ to change the rate at which it's operating. So I think that the use of wireless communication inside the body for artificial organs, for sensing, for collecting information, for making control decisions about devices operating inside the body is a very powerful paradigm. And then, of course, having sensors around our body.
As a last question, we're running out of time. Do you see us ever pushing into terahertz bands, and what would be the challenges and opportunities there?
So I think that we will push into terahertz bands. We are already pushing into millimeter wave, which is actually, there was a lot of skepticism about whether we would be able to do that, but we have been able to build systems using millimeter wave. My personal opinion is that millimeter wave is going to be a niche part of Wi-Fi and cellular because it's very challenging to do the massive MIMO that's needed to get a high range. So if we can only get short range, that's going to be a limited application of millimeter wave. And if we can get, but we will use millimeter wave at least for short range communication and in some places where we can do massive MIMO. Terahertz is, another level of complexity. It's much harder to do than millimeter wave. We don't have electronics that operate at those frequencies that are efficient and cost efficient and energy efficient. But I think that just like millimeter wave will be a niche part of the next generation of wireless, I could absolutely see terahertz being a niche part of a future part of wireless.
I'd like to thank Andrea for the wonderful presentation and the insightful discussion on these questions. Special thanks to all of you as well for taking time to attend and participate today with your many questions. We'll do our best to still answer a few of them or some of them online. This webinar is recorded. It will be available in a few days on webinar.acm.org. You can find announcements on upcoming webinars and other ACM activities at learningacm.org and acm.org. Please take some time to fill out a quick survey with feedback or suggestions for future topics and speakers. You should see the survey on your screen. And again, on behalf of the ACM, Andrea Goldsmith, and myself, Marco Gutese, thanks again for joining us, and I hope you will join us again in the future. This concludes the webinar. Thank you.